So welcome back, everyone, to the research prep course held by STEM for Tomorrow. So today we'll be talking about material science part 2. So in the last session, we talked about atom basics such as protons, neutrons, and electrons, the periodic table, valence electrons, electron configuration, and also the 4 quantum numbers. And then we touched a little bit on the bonds. So last session, we had a lot of stuff on the atomic scale, but this time we're gonna go a little bit bigger, okay? And we're gonna see what happens when we put a bunch of these atoms together and what kinds of structures can they form, all right? So first, a little bit of review. I know I went over this slide really quickly last time. Okay, please don't annotate, okay? So let's talk about bond energy. So whenever two atoms come together or two molecules and they form a bigger molecule, it will either release energy or require energy to be inputted. So bond energy is going to be the sum of all of the parts minus the sum of the energy of the whole molecule. So if the bond energy is positive, it means that the material is stable. So a positive bond energy means that the sum of the energies of the parts is greater than the energy of the whole material. So for example, if I have two oxygen atoms, then if the bond energy of O2 is positive, that means that the sum of the two energies of the oxygen atoms is greater than the energy of the whole molecule O2, which is the air we breathe. All right, so we want bond energies to be positive so that the materials are stable. And negative bond energy means that it's unstable. So if you just put in a little bit of energy, if you just like perturb it a little bit, it might completely fall apart. So we don't want that. All right. Come on, my computer is. Sorry, I think I have some technical difficulties again. Oh, can you guys hear me?
Very echoey.
Or what about now? Is it fine now? Can you guys hear me better?
Yeah.
All right, sorry. I think whenever I turn on my camera, it lags a lot. So I'm just gonna keep my camera off. So yeah, basically we want, if we want to form new materials, we want to make sure they have a positive bond energy, or else they're not gonna be viable or stable, okay? So let's dive into some new material, okay? So let's talk about crystal structures. So in real life, like there are a bunch of crystals, right? You can either have ice crystals or crystals like diamond. And crystal structures are basically regularly occurring patterns in the atoms or molecules that the atoms and molecules form in a material. So a crystal structure means that there has to be some sort of repeating pattern. So here on the right, you can see I have the atomic structures of both water and ice, okay? So water you can see is just a bunch of H2O molecules sort of floating around. But ice, you can see it's in a compact crystal, okay? And so water does not have a crystal structure because there's no unit that is repeating because all the molecules are sort of jumbled up and sort of random, right? But in ice, all of the entire crystal is repeating. I can take one of these hexagons, okay, and then repeat it like however many times I want to form however much ice I want, okay? So ice will have a crystal structure because it can form a pattern, but liquid water does not. And the smallest group of atoms that constitutes this repeating pattern is called the unit cell or primitive cell. So basically, if I cut out one piece, like some tiny piece, the unit cell is going to be the smallest piece, so that if I take this and layer it in all 3 dimensions, I will get ice, or we get the entire structure. So as an example, how do I draw on here? Okay, as an example, suppose I'm in 2 dimensions, okay? So if the unit cell of something is a square, okay, with like 1 atom inside, then basically what happens is that you make a bunch of these unit cells and you keep repeating this infinitely. And of course, there are atoms in the middle. So the final structure will just be a bunch of atoms in the middle of all of these squares, okay? If the unit cell is instead a hexagon with, let's say, an atom here and here, then, let's see, do I have space over here? If we just draw a bunch of these hexagons, you can see that we can make these hexagons regularly repeating, right? And then we just put all of these atoms in. So basically, this is sort of like a geometry problem. Once we have the unit cell, it's going to repeat in all 3 dimensions. So here I only use 2 dimensions, but in real life, it's going to repeat in all 3 dimensions into whatever material we want. Okay, does that make sense to everyone? So if you have any questions, then just ask in the chat or use your mic. Okay. So can I move on to the next slide? All right. So let's talk about some terminology. Okay. Hold on, let me erase this. Okay. Let's talk about some terminology. So the lattice constants are the 3 dimensions which form, what grade is this for? This is for, the targeted audience is grades 6 through 10. Okay. I think anybody will be able to understand because it's sort of like patterns and geometry. So the lattice constants or lattice parameters are the 3 dimensions or directions which form the unit cell. For example, if my unit cell is a rectangular prism, let me draw. My unit cell is like a rectangular prism like this. And the lattice constants are going to be this length right here, this length, and this length. And we usually denote them by A, B, and C. And of course, the unit cell doesn't have to be a rectangular prism. It can be like a triangular prism, or it can be some sort of weird hexagon thingy or hexagonal prism like this. The unit cell can really be whatever you want. Or I should say, not whatever you want, but there are many different types of unit cells and many different shapes. And once again, the unit cell or primitive cell is the smallest group of atoms that constitutes a repeating pattern. And if orthogonal means perpendicular, so if the unit cell is sort of a rectangular prism or a cube or something like that, then the lattice constants are said to be orthogonal, meaning perpendicular, right? But in this structure over here, the lattice constants are not perpendicular, all right? And so many common structures have perpendicular lattice constants or lattice parameters, and many do not also. So we'll talk about both of them, okay? So let's talk about some of the most common crystal structures. So there are obviously a bunch of crystal structures because there are a bunch of unique materials, and then you can be really creative and form like a bunch of different crystal structures, but there are a few that are the most common. So the first is a simple cubic, okay? So basically, let me see if I can draw. In a simple cubic crystal structure, the unit cell is a cube, okay? This is my unit cell. And then the atoms are arranged at the, just say, corners of each cell. So basically, if we want to show one unit cell, we just draw the cube and we pick one corner. Because we don't want to include atoms on all 8 corners, because otherwise, when you repeat this unit cell in all 3 dimensions, you can imagine drawing cubes on top, you're drawing cubes to the side, right? or in all three dimensions, then this atom, each corner here is going to be the leftmost corner, the bottom left corner of one of these cubes, right? Because you're theoretically drawing like a bunch of cubes. Like ideally you have infinitely many cubes. So the unit cell will just be a cube with one atom in the corner, all right? And so in the end, it's going to look like, basically, if you have a grid, hold on. You have a grid like in 3 dimensions. Then there are going to be atoms on each of these intersections of the axes. Does that sort of make sense? In all of the corners of these cubes, okay? And fun fact is that if you take all of these corners and think of atoms as huge spheres, then imagine like these spheres are like balloons, right? You can expand them as much as you want, but then they're going to intersect each other. So if you think of like you're packing spheres inside a box, then this method of packing spheres, you have 47.64% void space, which means you have 47.64% empty space if the spheres are this big, okay? But we can actually do a lot better, okay? We can get a lot less void space. We can fill in some of this empty space over here, okay? With different types of crystal structures. So, how do I, the next slide. So the next type of crystal structure is going to be the face-centered cubic, or FCC. So the previous one was simple cubic, or SC. This one is FCC. So once again, the unit cell is a cube, right? But this time, the atoms are arranged at the corners, but also the centers of each cube face. Okay, so basically, if this is my unit cell, then I have an atom in each corner, and I also have an atom on each face, on the center of each face, okay? So it's going to look something like this. You have atoms in each corner, and then also on each face. And so in this face-centered cubic structure, you're going to have 25.95% void space, so space like in between all these spheres. All right. So this is FCC, face-centered cubic. And the reason it's called face-centered cubic is because there are atoms in the center of each face. So there's 6 faces on a cube, right? And so there are atoms on each of these centers. And I want to re-emphasize that the unit cell only contains 2 atoms, not like all of these, because we're going to repeat all of these cubes, right? And so we're going to, these 2 atoms are going to be sort of repeated in all 3 dimensions, okay? So are there any questions so far on these crystal structures? All right, so let's go on. Void space is just, void space is basically the space in between, like empty space not covered by these spheres. So you can imagine you're packing a bunch of spheres inside these cubes, and then the void space is the empty space here, okay? So ideally you want to minimize the amount of void space, because in real life, when you have atoms, atoms are only really small. They're not going to be as big as these cubes or these spheres shown in this picture, but these atoms are going to interact with one another, okay? And these interactions are sort of like spheres, because you can sort of think of it as a sort of region where the atom can exert a force on another particle, okay? Because you can think of it as like you have an atom in the center, and then you have a tiny sphere where this atom can interact with other particles inside by attracting or by any force. And so atoms naturally want to take up or want to minimize the amount of void space that is not inside any of these regions, okay? So this is sort of like a geometric interpretation, okay? It's also fun to think about. So the next type of crystal structure is going to be the bodied centered cubic, or BCC. So once again, the unit cell is a cube, but now the atoms are arranged at the corners of each cube. So once again, at the corners, but instead of an atom being on the face of each cube, there's now one in the center of the cube. So there's a difference between the center of the faces of the cube and the actual center of the cube, right? So basically, you can see in this diagram, you have atoms in the corners and then just one in the center. So the unit cell is going to be this cube with an atom in the corner and an atom in the center. Okay, and you can see here there's this huge sphere in the center and then a bunch of little spheres in the corners. And here there's actually 24.8% void space. All right, and it's slightly less than 25%. So BCC is a little bit more efficient. All right, so are there any questions on BCC or any of these cubic structures or lattice structures? All right. So next, before we move on to two-dimensional materials, I want to mention that these structures, like these cubic structures, have unit cells that are cubes, obviously from the name, right? But not all unit cells are shaped into cubes or even rectangular prisms where the where the sides are perpendicular to each other. In two-dimensional materials, especially, usually the unit cells aren't orthogonal or there aren't cubes. Okay, so it's a bit weird. So let's move on to two-dimensional materials. So two-dimensional materials are really cool materials, and you may have heard of this in school, but two-dimensional materials have only been studied for about 10 or 20 years. Actually, you know, the first two-dimensional material is graphene, and it was only discovered in 2004, which was like after I was born. So it's pretty recent. So two-dimensional materials are materials just a few atoms thick. So it can be either one atom thick exactly, or maybe like 2 or 3 or 10 or 100, but not like billions and billions of atoms thick like regular objects. Okay, and surprisingly, based on their based on their thinness, they're actually surprisingly strong. So a sheet of graphene, you may have heard that graphene, this material here, if you have heard of it before, it's actually about 100 times stronger than steel. All right, so who has heard of graphene before in like some context? Right, so a bunch of people are raising their hand. Right, so graphene is basically the first two-dimensional material discovered, and it's made up of a bunch of carbon atoms. So these are all carbon atoms, and they're bonded together in this hexagonal structure. So you can sort of see why this material, which is only like one atom thick, is really, really strong. Right, so someone said graphene is a one atom thick. Right, good. So graphene is a one atom thick structure, which is made up of carbon atoms arranged in a hexagonal lattice. And they're so strong because it's really hard to bend this material because it's made of hexagons, really rigid hexagons. And you're going to take a lot of force to remove one of these atoms or one of these bonds because they're packed so tightly in hexagons. So there's not much wiggle room. So the material is really strong. But graphene is by far not the only two-dimensional material. It's only the first. And although it gets the most it's the most buzzwordy two-dimensional material, there are actually a lot more two-dimensional materials, and some of them are actually better than graphene. So either stronger than graphene or have better properties than graphene. All right. And what's interesting is that two-dimensional materials are often semiconductors. So we'll go into why they're often semiconductors later, but semiconductors we rely on all the time, right? With computers and phones. semiconductors are what makes silicon chips and computer chips. How many atoms thick is graphene? Graphene is actually only 1 atom thick. But you can stack a few layers of graphene on top of each other. So you can have like 2 or 3 or 10 or 100. But if you stack millions of layers on top of each other, it just becomes graphite, which is what your pencil lead uses. So there's actually a really cool trick you can use to isolate graphene at home. What you can do is take some pencil lead, which is made out of graphite, unless you have like a really old pencil. So make sure you're not using a mechanical pencil, but just like a regular wooden pencil, like number 2. And then what you want to do is you want to take a piece of tape, and then you just basically you try to tape some of that graphite off. Then you keep sticking the tape together, because when you first initially tape the graphite, you're gonna get millions or 100 or thousands, but a lot of layers of graphene. All right. But if you keep sticking the tape together, it's going to pull apart the layers. If you do it enough times, you're going to have graphene that's maybe 10 or 20 layers thick, which is really amazing considering you can do it with your hands and just how small atoms are, right? So basically, you can have either 1 layer of graphene or you can have multiple. But keep in mind that if you have multiple layers of graphene, then the layers of graphene must be stacked on top of each other, but there must be there must be enough space between the 2 layers, because if you stack like 1 layer directly on top of this other layer, then it's not going to become graphene anymore. You have to put this significantly above graphene, above the other layer. Usually you have to put it about 3 or 4 nanometers above graphene. I know a nanometer doesn't sound like much, but it's actually a lot when you consider the size of all of these atoms. All right. So maybe if this is my graphene layer and I wanted to stack another one on top of it, then the other one would have to be somewhere at the top of the screen. Okay, so that's how far you need to keep them apart. Otherwise, you would have too much interaction between the different layers. That's not what you want, because it ruins the purpose of a 2-dimensional material. All right. So are there any other questions so far? So I'll wait like a few seconds. Alrighty, so let's move on. So now I want you to, I have a little exercise for you. So remember that graphene has a hexagonal structure, so something like this, where these are carbon atoms. So I want you to find what is the simplest unit cell of graphene. All right, so before you guys start, the unit cell is only, remember it's 3-dimensional, but since graphene is only 1 layer thick, just treat it as 2-dimensional, okay? So suppose I want to find a 2-dimensional unit cell of graphene. All right, so basically try to find a repeating unit that will, like, when you transfer it in like all 3 dimensions, then it will form this entire structure. So someone said just the hexagons. So that is the first thing somebody would think of. But it's actually not the simplest cell. So let's give this a try. Okay, what if it's just hexagon? See if I can draw here. We just have 1 hexagon as our unit cell, and suppose we have I don't know, an atom right here. Okay, if we had an atom, if this was our unit cell, then let's draw this. Okay, so we can extend this hexagon in a bunch of dimensions. Let's just draw a bunch of hexagons. But take a look over here, okay? This corner right here. We know that a carbon atom has to be here, right? But how is a carbon atom going to get over here? Because we only have like our definition of the unit cell was we had 1 atom in the bottom left corner of the hexagon. But this is not a bottom left corner of any hexagon, right? So we're not going to be able to have an atom here. So good try. That is the most intuitive thing. Hexagons are the most intuitive thing, but that won't exactly work. So someone else said, what about the line segments? So you're actually getting a bit closer. So I think what you mean is like these line segments, right? You can see that all of these carbon atoms are going to be sort of paired up, right? So you might say, oh, okay, let's just take these line segments. All right. Let's just take these line segments which have two atoms on them, and let's call this our unit cell. Well, the thing is, this is only one-dimensional, so we're not going to be able to go up. So we need a unit cell that's two-dimensional, but you're on the right track. The unit cell does involve grouping these atoms sort of like this, okay? So anybody have any other guesses? So you're getting closer. And also the unit cell, you want when you're telling somebody like the unit cell, you want to specify the shape and also where the atoms are, okay? Z's, what do you mean by Z's? I'll allow you to draw. So can you sort of draw on, can you sort of draw on here? Does it work? So, are you saying like, okay. So sort of this thing. But remember, you want this to be rigid because you're gonna want this to repeat. Okay. You want it to be sort of like a diamond shape or something like that, or hexagon that can repeat itself. All right. So somebody said this. So let's see if this works. Okay. So remember, the unit cell can't really be a circle because if you try to repeat the circle, like you can't really do it, right? Because there's going to be empty space. So you're getting a little bit further away. Okay, stick with the two atom thing. Try to pair up these atoms. So I'm going to give you a hint. Okay, the unit cell contains two atoms. So now we just suppose we choose these two atoms. Okay, now we have to find the shape of the unit cell. What shape will we have? What shape is the unit cell so that when you repeat it, it's going to um make all of these atoms. Stop drawing hearts. Okay, so I'll just give you the answer, okay? So it's clear all. So it's actually a diamond shape. So this is the unit cell, this red diamond right here. Remember, you can't just draw it like a random circle over these atoms because a circle is not going to be able to repeat itself in all directions. But this diamond, look over here, this diamond containing these two atoms, when you repeat it, each of these unit cells is going to contain two more atoms, right? Does that sort of make sense? And you can see that this atom, this unit cell is repeatable because there's no empty space in between, right? So you can think of doing this infinitely or like in all directions. And then eventually you will get all of the atoms. All right, you can just see from these blue unit cells, neighboring unit cells, that all of this does work. There are two atoms in each, and they're all in the center. All right. And I want to point out that this unit cell is two-dimensional, but all materials in real life are three-dimensional. So if you want, except for like one layered graphene, but if you want to stack a bunch of layers on top of each other, then you're going to have a unit cell that's sort of like a diamond on the base, then something really tall, okay? So you're gonna have a unit cell that's something like this, and your two atoms are down here. Because then your other atoms in the next layer will be way up here, okay? Because you don't want them to be too close to your first layer, okay? So does this make sense? Does it make sense to everyone why the shape of the unit cell is like a diamond? So are there any questions? All right. So let's move on. Let's clear all the drawings. So let's move on to doping, okay? So the definition of doping is the addition of foreign substances in the material. So you may have heard of doping as from like sports or athletes, where um, athletes, I think this is illegal, but athletes are gonna inject stuff into their body to make them perform better. Well, this is exactly what this means in when we're talking about atoms. You basically have a material and you inject extra stuff, whether it be atoms or charges or electrons, to make it perform some certain task better. Okay, and I'll show you an example of what this means. So the first type of doping is charge doping, okay? Charge doping is how transistors and computer chips work, okay? It's why you can have a switch that turns between, that switches between 0 and 1. That's how computers work. So how this works is that you know that computer chips are made of silicon, right? Silicon chips. Silicon has 4 valency electrons, okay? It's in the same group as carbon and all of those elements. So here's silicon. And they're covalent, they're gonna be not covalently bonded because it's like a semi-metal. So it's gonna be metallically bonded to all of these other silicon atoms. So ignore this phosphorus right now, I'll get to what this means. So if you have a bunch of silicon, then they're going to be metallically bonded, and all of these electrons are going to sort of float freely, okay? But one type of doping is called N-type doping. The N stands for negative. So it's when you have an element like phosphorus, 5 valence electrons, that's added to the silicon, okay? And the reason why we use phosphorus is because phosphorus is about the same size as silicon. So it's going to fit into this lattice without doing any significant damage, okay? But phosphorus has 5 valence electrons instead of 4. So you can see that there's this one electron, one extra electron, right? So there's just this one extra electron just floating around randomly, okay? So there's an extra electron. What about the other type of doping? P-type doping. It's when you have an element like boron, which has 3 valence electrons added to silicon. So here you can see that boron only has 3 valence electrons. So there's like a hole here where there should be an electron, but there's not an electron. So instead of looking at the lack of the electron, let's think about the hole. Okay, let's try to imagine that the hole has a positive charge. Okay, so you can think of it as in N-type doping, you have an extra electron with a negative charge, and in P-type doping, you have an extra hole with a positive charge. Does that make sense? So these two types of doping, N-type and P-type, have everything to do with how transistors work and how you can create bits with zeros and ones in computers. Okay. Yeah. So N-type doping and P-type doping. Are there any questions so far? And I want to say that these materials, even though we use N and P for negative and positive, these materials are actually neutrally charged because phosphorus, although it has 1 extra valence electron, it has 1 extra proton as well. Okay, so the whole thing is going to be neutrally charged, but there's just an extra electron floating around. What happens when you put this substance with this substance together? Well, you get something called a PNP transistor. So it's when you have a boron over here, the boron doped silicon. So basically silicon, but with a little bit of boron in it, and then phosphorus over here, and then boron over here. So this stands for positive, negative, positive. And what happens? Remember I said that the boron over here has a hole, right? Wait, sorry. This is supposed to be phosphorus is in the middle. So sorry, boron, phosphorus, boron. Okay. So remember how I said that boron has an extra hole, right? And phosphorus has an extra electron. So what's going to happen is that the electron is going to fill the hole. So if you have phosphorus right here, phosphor, then boron on the sides. So there are a bunch of these extra electrons over here, right? But there are a bunch of these extra holes in the boron. So the electrons are actually going to fill these holes up. And what's going to happen is that electrons are going to leave the center, which makes this positive. All right. And oh, okay. And the electrons are going to enter these holes, which makes these two negative. All right. Wait, sorry. I got this mixed up. So boron is actually, this is right. The slide's right. The boron is actually in the middle. So boron is in the middle, and then phosphorus is on the sides. So there are a bunch of electrons here. There are a bunch of holes in the middle. So positively charged holes. And then these electrons are going to move into these holes. So there are going to be extra electrons in the middle. So it's going to be negatively charged. And there are going to be less electrons or more holes over here. So it's going to be positively charged on the sides. So this is a PNP transistor. Positive, negative, positive. So here what happens is that electrons can't move back at this point because remember, electrons are negatively charged. So there's sort of this positive barrier that's going to repel, or this negative barrier that's going to repel the electrons if more try to enter in. Okay. So in this case, this transistor is in the off state, so it's going to output a 0. But what if you apply a positive voltage across the middle, across the base? So you apply a positive voltage. Then what happens is that electrons, remember electrons are negative, right? So electrons are going to get sucked into the positively charged voltage because a positive and negative attract, right? So even more electrons are going to get sucked in here, and then they're going to eventually form a complete circuit. So they can't actually leave here because there's no actual wire going out, but it's just the voltage. So essentially the electrons are going to go all the way. So it's going to form sort of a complete circuit. All right. So when the transistor is off, there's going to be no circuit. And when the transistor is on, there's going to be a complete circuit. So it's going to be a 1 this time. So basically what we just did, this transistor right here, is basically a really small way or a simple way to turn a switch on and off. It's basically a switch, right? And the only thing you need to do to turn it on is apply a very, very small voltage. And then you're going to suck some electrons to the other side. And then you can have some detectors over here that can detect whether there's a voltage or not. So that's how transistors output zeros and ones. Okay. Does that make sense? So are there any questions so far on how PNP and transistors work? What's the benefit of using a PNP over a normal switch? So PNPs can be made extremely small, okay? Take a look at this. These are atoms. Like these are you can make these like 50 or 20 to 50 atoms thick. So extremely small. But if you have a normal switch, you can't get it that small. Okay? So some of you guys may know a law called Moore's law. So I'll type in the chat. It's Moore. And Moore's law basically says that starting like the 70s or the 80s, the efficiency of transistors in computer chips, so basically the size of transistors, will shrink by a factor of 2 every 2 years, right? Which is incredible. You can think of like I don't think anybody would have imagined that the efficiency of transistors would grow exponentially, meaning they double over a certain period of time. No, it's actually 2. Doubles every 2 years, not 10, which is actually incredible, right? Just 2 years ago, computers are like twice as fast as they were 2 years ago, which is pretty amazing. So the problem is that you can keep shrinking these transistors smaller and smaller and smaller, right? But as I said, these transistors are only like 10 to 50 atoms thick. So you can't really get much smaller than that. You can't really have like a 1 atom transistor, right? That's not really a thing. So if you go too small, then you're going to hit a barrier, okay? So you're going to have to do something innovative or something new to be able to bypass this barrier, all right? So Moore's law is sadly coming to an end in the near future, maybe in the next 10 years or 5 or 10 years. But there are certain ways to get around it and form new types of transistors, okay? But I just decided to bring up Moore's law because it's really amazing how much computer chips have progressed over the years. All right. So now there's another question. Okay, can you just explain everything again? Okay. So basically, you have phosphorus doped silicon on the left and the right, and then boron doped silicon in the middle. So in the boron doped silicon, there's a bunch of extra holes, and on the side there are a bunch of extra electrons. So the electrons are going to fill in these holes, and since there's a lack of electrons on the side, they're going to be positive, and there are more electrons in the middle, which is going to make it negative. Okay. So then, in order to turn the transistor on, you apply a voltage over here, which pulls the electrons over because electrons are negative, right? So they're going to be attracted to a positive voltage. So then the electrons are going to flow across, and then you can detect it with the current. Well, you can detect the current, okay? So that's basically how a transistor works. And then NPN transistors are basically the opposite, or same thing but reversed. So NPN is where you have phosphorus in the middle, and then the boron on the sides. Okay, and it's basically the same thing, except instead of a positive voltage, you have a negative voltage. Then the electrons are going to be flowing in the opposite. Okay, so those are the two types of transistors. And so another type of doping is atomic doping. So before we did like charge doping, where we manipulated the charges to make some of these positive and some of these negative, and then use that to exploited that to make transistors. But here in atomic doping, we're just adding new atoms to a material and seeing what happens. Okay. So there are two types of doping: substitutional and interstitial. So substitutional doping means you basically have a structure and you literally just replace one of the old atoms with a new atom. So for example, let's say you have graphene, okay? Where's graphene? Here's graphene. So you can literally just replace one of these with another atom, let's say nitrogen. And you can do this on whatever period you want. So you can vary the concentration of the dopant. So the dopant is a new atom. In this case, it's nitrogen, but you can vary the concentration. So you can make it repeat every 1 unit cell or every 2 or every 3 or 4, however many you want. And when you dope a material, you will actually, most of the time, you will create new properties that are often more desirable, okay? So the second type of doping is going to be interstitial doping. So basically in interstitial doping, a new atom is added and the old atom is still there. So you basically just add another atom on top. So you can add it in the middle here, or you can add it like on top of this atom or in the middle of the bond over here. There are different types of things you could do. Once again, whenever you do doping, you are likely to create a new material with better properties. All right, so let's talk about how we can, in this last 2 minutes, let's talk about how we can tell if a material is a semiconductor. So let's suppose we have a material and then we doped it, okay? We added some new atoms. So we can either do this like in real life, where you actually create the material, or you can do it with software. But now that we have the material, how do you determine if it's a semiconductor? How do you determine if it can replace silicon chips and bypass Moore's law or something like that, right? Well, a semiconductor by definition has a conductivity between that of a conductor and an insulator. So it's sort of sometimes conducting and sometimes insulating. So current semiconductors are silicon, which is used in silicon chips, obviously, germanium and gallium arsenide. And people are actually exploring how these two latter materials can be used to replace silicon to make computers even faster. But we can tell if a material is a semiconductor, especially two-dimensional materials, from the electronic structure. Okay, and what is the electronic structure? Well, the electronic structure, or the band structure, is essentially the plot of the energy levels of electrons in the material. As the electrons evolve through different states called K points down here. These are called K points. So you can just think of these as states, okay? And the band structure is a diagram that plots the range of energy. So each one of these lines right here, these curvy lines, is a band, meaning it's 2 electrons or 1 orbital, okay? So basically, suppose you have graphene, right? You have 2 carbon atoms. In each of these carbon atoms, you take all of these orbitals and you plot their energies, okay? And so you have this funky structure called the band structure. And you can actually remember how electrons in each orbital, you can have a spin up and a spin down electron. Well, you can actually split the band structure into both the spin up and spin down components. So you can create 2 separate band structures. And in these 2 cases, each band is not 1 orbital, but it's just 1 electron. So either spin up or spin down. So we have a band structure. Suppose we have a band structure. So we can, the easiest way to calculate the band structure is through sum here. But if we have a band structure, how do we tell if it's a semiconductor? Basically, the bands with positive energy are conduction bands up here, are conduction bands, and the bands with negative energy are valence bands. So remember how you have valence electrons on the edge? Conduction electrons are basically all the electrons that aren't valence electrons. So all of the electrons in the core of the atom, all right? So in order for there to be a semiconductor, there must be a gap between the valence and conduction bands. So a gap right here. So in this case, there was no gap because you can see that the bands sort of intersect. There's no gap. But if there is a gap, then it's a semiconductor, because if you have the electron that's, say, at -5 electron volts, so this is energy, -5 energy. And if there's a gap, it means that there's no way for this electron to jump into the conduction band from the valence band unless you input a significant amount of energy, right? But here, since there's no gap, if we're at state K, then if you're an electron in the valence band, you can just jump up to this conduction band right here with barely any energy, right? But if there is a band gap, then it requires energy to bump it up, bump an electron from the valence band to the conduction band. And so the reason it's a semiconductor is because electrons are more controllable. It's not always a conductor because the electrons can't just float freely. You have to actually input energy in order to move electrons from the valence to the conduction bands, or vice versa, right? So let me give you an example. So here is graphene. This is the band structure of graphene, right? But what if I dope it with nitrogen? So here are like different types of nitrogen atoms, and you can see that these people just added them over here, and now there's actually a band gap. There's actually a gap. The bands do not touch. So suppose that you're an electron over here. I actually have to input a significant amount of energy in order to bump it up to this band right here. So here it looks like it's about 1 electron volt or 1 energy or whatever. So this makes it a semiconductor because it's not, the electrons can't just float freely, right? That's just a conductor. But we don't want the band gap to be too big. We don't want like the bands to be way up here, because otherwise you have to input a whole lot of energy in order to get the electron from here to here. That's going to make it an insulator. But usually this never happens, okay? So usually any band gap is significant. And usually you're not going to have like too big of a band gap. That's usually not a thing. All right. And as I mentioned before, doping is a very common method to induce a band gap, to open up the band gap. For example, graphene here, right? This is pristine graphene, pristine meaning pure, so no doping. But if I do nitrogen doping, then there's going to be a band gap. So this is a semiconductor right here. While graphene over here is just a normal, regular old conductor. The graphene itself can't really be implemented in computers or silicon chips or replace silicon chips, but this material at least has some potential because it's a semiconductor. And obviously there are a bunch of other properties. You can't just use any material that has a band gap. All right, but that's more complicated. All right, so are there any questions about band gaps or semiconductors? All right. So what's interesting is that now researchers are actually experimenting with two-dimensional materials. And they think that in the next 5 or 10 years, a two-dimensional material could be made viable that could replace silicon. Okay, make computers even better, or transistors even better. And actually, in the past month or so, Samsung actually created a new material, two-dimensional material, which has a band gap, so it's a semiconductor, and they're actually working to implement it in like their computer chips for all their electronics, which is actually really cool. So yeah, so that is material science. Basically, the gist of material science is you just devise new materials that exhibit certain properties. And usually the properties we want are semiconducting properties because they're really cool and they have really cool applications. All right. So this is the first session or the first topic of the research prep course held by STEM for Tomorrow.